Hey guys, in this series of videos we'll start by looking at Coulombs Law, and then we'll look at spherical charge distributions, then we'll look at some applications of Coulombs Law, and we'll finish with an exam-style question.
So, Coulombs Law, what is it? Well, Coulombs Law is actually just the name we give to the force law between charged particles. So just as we had, Newton's law of gravitation for gravitational masses, we have Coulombs law for charged particles. So how can we actually work out the force that two charged particles experience due to each other? We came up with all those field diagrams in our previous set of videos, but how can we actually talk about what that force actually is, put a number to it, without needing to go into electric field strength, etc. So we just have two charged particles. That's why I've just put these black spheres here, because I'm not going to say whether they're positive or negative. We're just going to say that the charge is Q1 and Q2. So let's write that down. So Q1 and Q2, particle 1's got charge Q1, particle 2's charge Q2. I'm going to say that they're centres, because really, actually we're going to say that this works, we'll see that in a moment, with spherical charge distributions, but this would work just as well if these were charged spheres instead of being charged point particles. So they're the point particles are the centres of the spheres, if that's what they are instead. It's going to be a distance of r apart from each other. And then the final thing is, we're going to say they're experiencing a force of F. Now, I'll say that's attracted towards each other just because, but actually there's no need to do that. It could also be repulsive. That's one thing we have to remember about about charged particles, that they can repel each other as well as attract each other. And really that's going to depend on whether the charges are both negative or both positive, or a mix of both. So if we actually want to work out the force that they experience, well, we've got all these things now. We've got the charge that they both got on them. We've got the force they're experiencing, and we're saying what we want to find. We want to find the force they're experiencing, given that they're a distance of r apart from each other, and they've got these charges. Well, it's actually a really simple formula for point charges. Remember, it's a simple formula for Newton's gravitational law as well. It's the same here. It's the same kind of law, in fact, as well. So it's a really simple formula for point charges. And also a really simple formula for spherical masses. But the thing is, we've got to remember, on some scales, basically everything is a point particle. If you think about it, on the scale of a galaxy, the solar system is definitely a point particle. Kind of on the scale of a universe, the galaxy could almost be a point particle if you're thinking out far enough. So you really don't have to be talking about protons and electrons here. If you're allowed to zoom out far enough that you just look like you're left looking at a dot, then this formula works here. So that's kind of how it works. So what are the big qualities of this force law? We find that the force between 2 point charges is proportional to the charges of the particles. What does that mean? We're going to say it's just proportional to, it's got to be proportional to Q1, it's got to be proportional to Q2. The only way that works is if it's proportional to Q1 times Q2. So for this to work, we're going to have Q1 times Q2 in there somewhere. That's what that means. The next thing we need to say is that it obeys an inverse square law, which means it's proportional to 1 over r squared, where r is the distance between the particles there. So it's proportional to 1 divided by this distance squared.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the SnapRevise smiley face. Join me today, and together let's make A-level physics a walk in the park.